Okay, so welcome to this session. So we are going to continue with the previous problem we had. So for problem number 4, we can see here a truss that is loaded as shown. So we are required to determine the stresses members BC, BD, and BE. And then we are going to indicate the type of stress. So in this problem, we need to go over with method of analysis in order to come up with the internal forces of BC, BD, and BE. And then we'll just have to consider the cross-sectional area to solve for the stresses. Okay, so the first step here, perhaps you can do it by method of sections or method of joints. So for BC, we can get right away the force on that member because it is obvious that in joint C, so at joint C, you can see here that there is only one vertical. Okay, so there's only one vertical here. So we're gonna use joint method to solve for BC, and obviously BC is just equal to 60 kilonewton, obviously. So if we're going to isolate this, okay, perhaps we can zoom it. So we can isolate this portion, and obviously there is no other vertical here, so we can just say that member BC is a tensile because it must have to resist the 60 kilonewton, and it will go against its direction. So your BC here is a tensile. So we can place it there. BC is equal to 60 kilonewton tensile. And then we proceed to the other unknowns, BD and BE. So for BD and BE, we can just use the whole structure and then cut section. Okay, we're gonna cut section here. And consider the left portion. Say this section is, so we can name that as AA. So at AA, we will just neglect this right portion and focus ourselves on the left portion of this truss. So this will now involve the reaction at A here. So we're gonna place reaction at A so that we will be needing the reaction at A. And reaction at A could be solved by summation moments at H. So summation moments at H is equal to 0. So start with a counterclockwise moment 80 times 2 minus another counterclockwise moment that is 60, which is 6 meters from H, and then a clockwise RA times 8 equal to 0. So here we can get the value of RA. We have 65 kilonewton for RA. So all we need is RA, but we need to ensure that RA is correct by our check mechanism through the other equilibrium equations like summation forces vertical. See our check mechanism, we're going to take moments at A is equal to 0. So first we have 60 times 2 plus a clockwise 80 times 6. Say we have here a reaction. Okay, I'll just assume it to be going upwards. Say this is RH. So your RH will now be counterclockwise. So that is minus 8 RH is equal to 0. So RH can now be solved. So we have here a value of 75 kilonewton. So we are now ready to check that by summation forces vertical. So all we have to do is to add all positive or upward reaction, say RE and RH. RE is computed as 65 and RH is 75 kilonewton. We deduct the two downward force here and it should equate to 0. So if we have a correct reactions computed, and really it would equate to 0. So now that we are assured of our reaction, we can now place here what we need, which is the RA. So we have here RA is equal to 65 kilonewton. And then we are going now to isolate the cut section of the leftmost portion, say section AE. So we maybe place it here. See, at section AA, we're just going to copy the truss. So notice that these three members here passes through your cut section. Say that is BD, BE, and CE. So what we do is to assume directions for these forces. Say let us have a compressive BD, tensile BE, and tensile CE. So all of these arrowhead are just an assumption, okay? Anyway, if you have a misassumption on this, your equation will just tell you if we have a negative result in the equation. Okay, so we continue by completing all of the forces that are present on the leftmost portion of the section AE. So we're going to place all of the forces there. So what we do next is to solve for BD and BE. Now, what we do, the technique here in method of section, or what we call equilibrium of non-concurrent forces, what the technique here is to get a point wherein you can intersect two unknowns and then solve for the other one. So obviously, if I'm going to take moments at A here, say this is point A, BD and CE will eventually meet at point A. The consequence is there will be no moment arm for BD and CE. In that way, BE is the only unknown here, so we can right away get BE. But before we can proceed with that solution, of course, BE shall be resolved in a certain point. So you can resolve BE on the direction of arrowhead. You can resolve it at point, say point E, or you can resolve it at point B. Now here's the scenario. If I'm going to choose B as my location for BE, there will be two components for BE. Say this is BEX and BEY. So it will involve two BE, two components of BE, X and Y, because both has its corresponding distances from A. So if that is a scenario wherein if we are going to resolve it at B, then your BEX and BEY will just be situated at that location. So on the other hand, if we choose to resolve it on E, say we choose E, there will be two components here. Say this is BE Y and BE BEX. So notice that if this is the case, taking moments at A, BEX will again be intersecting your point of moment at A. So it will only involve a single force here, say BEY. That is why it is now much safe to say that it is more convenient to resolve your BE at point E rather than point B. So anyway, you can do whatever you want, whatever you may opt to, but for simplicity, I'm going to choose to resolve BE at point E. So if we're going to resolve that, of course, we need to determine the slope of your BE because the component will be dependent on the slope. You can express the components by looking at the slope in order to come up with the forces. So as we can see here, this is our BE, and by symmetry, the slope of AB is the same to that of the slope of BE. So all we need is to determine what are the involved vertical and horizontal slope. So obviously this is 2, and we need to determine this y slope here. So if we are going to have the half thrust here, we look into the dimensions. So the dimension, obviously, if this is the king post, this is a 4, and for the base, it is also 4. Therefore, the slope of this is 1:1, and therefore, whatever the vertical slope is, that is also equal to the horizontal slope of it. So if we have 2 here, therefore, this is also equal to 2. So obviously, we have here a 45-degree angle. Hence, the slope will be simplified to, say, 1:1, and then this is square root of 2. So knowing our slope, okay, so we can now write the component of this BEY by saying, and considering the slope here, 1, and square root of 2, we have BE is to square root of 2, which equates to BEX is to 1, and BEY as well is to 1 as well. So therefore, BEY pairing these two, therefore, BEY is just equal to 1 all over square root of 2 BE. Okay, we do not need to solve for BEX because again, if we're going to take moments at A, there will be no moment arm for BEX. Okay, so we are now ready to take moments at A. Say summation moments at A, we have a clockwise 60 times moment arm of 2, and BEY is also clockwise times moment arm of 4, and that would equate to 0. So we are after with BE, so therefore we can express BE by its slope, and then finally we can solve now for BE. So we will yield to a negative value of BE, which is 42.43. So what is the indication of negative? It means that we have a wrong assumption on the direction of BE. So by that, BE here, as you can see, BE is away from your joint. Okay, so this is your original joint. Take note of that. It is away from B. Okay, and therefore, it is assumed initially as tension. And since we have a negative here, we can now correct that one to BE is equal to 42.43 kilonewton, and it must be in compression. So we have already obtained now BE and BC in this truss. So we still need to get here the value for BD. Okay, for BD, we are going to use the same section AA, considering the left portion. So a while ago, we have intersected the two force members passing through this section, which is CE and BD. So CE and BD are intersected through moments at point A, so that the remaining unknown force here would be only BE. So this time, I'm going to intersect CE as well as BE, so that we will have the unknown BD. So the same procedure, or similar to that of the procedure a while ago, we intend to resolve BD at a certain point. So anywhere you can do that, but for for our convenience, I'll just have to resolve it at point D, so that BDY has no moment arm. So taking moments at D, BDY has no moment arm. So we will be just concerned with BDX. And BDX will be expressed in terms of BD using the same slope, because AB and BD has the same slope, 1:1, square root of 2. So we write BDX, that is equivalent to 1 all over square root of 2 of BD. And then we take moments at E. So moments at E, we have here clockwise 65 times 4 minus counterclockwise 60 times 2 minus your BDX times the moment arm of 4. This is 4 actually. And then just substitute the equivalent equation for BDX, that is 1 all over square root of 2 of BD. And eventually you can compute BD, and it will yield to a positive result equivalent to 49.5 kilonewton. So your initial assumption for BD is actually towards the joint here. So therefore, yielding to a positive 1 would mean your assumption of compression is retained. So hence, that is a compressive type of force. And then after we have already obtained all of the forces, we'll just have to apply this simple formula. Sigma is equal to P over A for BC, for BE, and for BD. So all of the members have the same or common cross-sectional area equivalent to 1,000 millimeters squared. So the obtained force for BC is 60 kilonewton. So that will be multiplied by 1,000 in order to express it in terms of Newton. So 60,000 divided by 1,000, we have 60 megapascal, and that is a tensile stress for member BC. And for member BE, we also place here the internal force 42.43 times 1,000 then divided by 1000, we come up with 42.43 megapascal. That will be a compressive stress. The same procedure for member BD. We'll just have to apply this and then substitute 49.5. So we have 49.5 megapascal compressive stress. So moving on to the next problem, we have here a series of heterogeneous tube that are attached, and all of these will be fixed on this restrained support here on the right portion. We need to compute here the value of P, or the maximum value of P that can tolerate the following stresses. Say in aluminum, we have an allowable stress of 80 megapascal. In steel, we have 150 megapascal. And in bronze, having 100 megapascal as an allowable for that material. So it is understood here that this setup is in equilibrium. So therefore, we have an excess reaction here to balance the force system. And as we can see, we have a leftward forces of 2p and 3p that will have a 5p going to the left and a rightwards p. So therefore, we will be needing a reaction on this support of 4p. Okay, so we'll have a reaction 4p here in order to have a balance in the system. So what we do is to determine the actual forces on each of this material and then apply the formula sigma is equal to P over A, considering all of the allowables on those material. So we are going to have here bisection method. Say we make here or construct three different sections that are passing through all of the material. Okay, so we consider first section AA for aluminum. Say at section AA, we have here the cut section with the P in it. Hence, it is obvious that P aluminum will be just collinear, to this and oppositely directed. Hence, aluminum is a compressive force. And it will just be equal to P. So at section BB, we have a cut passing through the steel. And of course, we need to consider all of the forces on the left portion. We have P and then 3P. Okay. Say a rightward force here, PST. So we perform this equilibrium equation. We have P minus 3P plus PST is equal to 0. Hence, PST will be equal to twice of P. So the type of stress here is actually tensile because PST will be away from the joint. Perhaps we can reflect it as a tensile. And the other a while ago is in terms of compression. So for the last section, we have a cut passing through the bronze material. So this time your section is considering the right portion for convenience. Say we have here P of bronze. So it is obvious that P of bronze is just equal to 4P and it is a tensile type of force. So all will be in terms of P here. So this is the time we are going to use the allowable for each of the material. First, we have the allowable for the aluminum. So we'll just have to use this formula applicable for the aluminum material. Say the allowable is 80 and the computed P of aluminum is simply equal to P. Okay. And then for the cross-sectional area, we have 200 millimeters squared. Hence, 200 times 80 is the value for P, which is equal to 16,000 Newton. So the value of P, if we consider the aluminum, is 16,000 Newton. So we do the same for steel. So the allowable for steel is 150 megapascal. We use the same formula. Substitute 150. The computed steel is twice of P. So we place that there. And the cross-sectional area for steel is 400 millimeters squared. We just place it there, and then we'll have a value for P. So we have a value of 30,000 Newton. And then we do the same for bronze. So it has an allowable of 100 megapascal. So we substitute. So allowable is 100, and then the computed bronze actual load is 4P. So we place it there, and then consider the cross-sectional area, which is 500 millimeters squared. So again, we can derive a value for this. We have now 12,500 Newton. So each of the allowables would give us a value for P, but the most safe value for P is the lowest among these values, and the lowest among these values is equal to 12,500 Newton. And this will be the maximum value of P considering those allowable of the material. So we do not choose the greater values because it would fail the other. Choosing this one, it would certainly fail the other material. Okay, so we always choose the lowest as the maximum value for P. So therefore, that's it for this problem. Okay, so we proceed to the next. Okay, so for this particular problem, this bar A, B, C, D is being suspended through the cables as shown. So D here, at point D, this bar is resting at point D on the smooth surface inclined at 50 degrees angle with respect to the horizontal. So our task is to determine the mass of the heaviest bar that could be supported by these cables. And if the cable is just only limited to 100 megapascal, and under that condition, the cable AB is 250 millimeters squared, and the cable at C is 300 millimeters squared. So anyway, the same principle, a simple stress uses this formula, sigma is equal to P over A. All we have to satisfy here is to have a W that is tolerable for the limits of within the limits of cable AB as well as cable C. Otherwise, if the weight of this bar is too heavy, one of these cable would fail and eventually it will rupture. Okay, so the basic step here is, of course, establish your free body diagram. So why do we need to do that? Because by and by, we are going to apply this simple formula on to cables in terms of W. Okay? The tensile cable in terms of W. And we have here two cables. So we are going to express TAB in terms of W and TC in terms of W under the limit where AB is limited to 100 megapascal and TC also is limited to the same value, 100 megapascal. So now we consider the free body diagram. First and foremost, this bar has a weight that is located at the centroid, or it is on the mid dimension of this bar. Say we label that as W. And then we have here the tension at AB, an inclined AB here. Say the angle is 30 degrees and an AB that is vertically upwards at point B. Say this is tension at C, and at D we have here a smooth surface. Therefore, there will be a perpendicular reaction here at the surface. Say this is reaction at D. And such surface is inclined with respect to the horizontal at 50 degrees. So here we will find a way to express TAB in terms of W and TC in terms of W as well. So we can do that through the three equilibrium equations, starting with summation forces X equal to 0. We have a rightwards TAB cosine of 30. And then first, we have the components of RD. RDX is actually leftwards. And then upwards RDY. And then RDX is RD sine of 50. And RDY is RD cosine 50. So the basis on that is 50 here. Okay. Say if this is the angle, perpendicular and vertical, this is also the angle. So in this case, this is the horizontal line. If this is 50 degrees, this is perpendicular and that is vertical. This is also your 50 degrees. Notice that 50 degrees is adjacent to the y component of RD. So therefore, this is RD cosine 50 and the other one is RD sine of 50 degrees. So we can go back to the summation forces X. We can continue now. We have here leftwards RD sine of 50 is equal to 0. Now we tag this as equation 1 for a while and then perform the other equilibrium equation. Say summation forces Y is equal to 0. We have upwards TAB sine of 30 degrees, another upwards TAB, less downwards W, plus upwards TC, and then upwards RD cosine of 50 degrees. So all of this will be equal to 0. So notice here that your equation contains AB, TAB, TC, and W, as well as RD. So in this equation, we cannot further proceed and we need to obtain another equation to simplify our equation. So for the meantime, I will tag this as equation 2. So we can form another equation. Of course, we wanted RD to be out of the picture if we are going to take moments, because going back to our objective, AB shall be in terms of W and C will be in terms of W. So obviously we are going to take moments at D in order for D to be out of the equation. So we take moments at D. First, we have TAB sine of 30 times moment arm of 6. By the way, this is 2, 2, and 2. And then another TAB times moment arm of 4 plus TC times moment arm of 2 minus W times moment arm of 3, or half of 6, because W is in the mid. So all of this will be equal to 0. Now, in order to supplement this equation, because as we can see, TAB, TC, and W are now present. So all we need is to supplement this equation so that TAB or TC will just be expressed in terms of W. So we can do that by equation 2, where in equation 2, RD here should be out of the picture. And we can do that because RD here could be expressed in terms of AB here. Say from this equation, we can have RD is equal to TAB cosine 30 all over sine of 50 degrees. Then we can utilize this equation by putting this or substituting this RD on equation 2. So we just copy this one, and then TAB, the W in it, and then the tension at C. So this time, we have to replace RD by this expression. So TAB cosine 30 over sine 50. So this is the RD. So we need to copy this cosine 50. And then all of this will be equal to 0. So let this be our, say if this is 3, so let this be our fourth equation. Now we can do elimination out of the third and fourth equation, but before that we need to simplify the terms because all of the TAB shall combine. Say this is 0.727 TAB, so we add to 1 here, so this is 1 TAB, so that is 1.727 plus sine of 30. So that sums to 2.23 TAB. So we just copy that W and TC. So this will now be equal to 0. Okay. So what about the third? So of course we also simplify that combining the TAB expression, the constant of TAB. So first we have 6 sine of 30 plus 4. So that sums to 7 TAB. So we arrange it this way also. So we write W here next to TAB, and then plus 2 TC is equal to 0. So we have the same sequence of arrangement among the variables here. Now we can use by elimination method. Say we wanted to eliminate first our AB, we can do it by multiplying it to this expression, 7 all over 2.23. So 2.23 will just be cancelled, and we will have the same constant as this top equation here. So we are going to perform a difference between these two equations. So we now have 7. Okay. copy this top equation and then distribute this 7 over 2.23. So we have here negative 70 AB and then plus 3.14 W, and we have here minus 3.14 TC is equal to 0. So we perform the difference. Okay, so this is cancelled. So this is 3.14 minus 3 is 0.14 W, and then minus 3.14 plus 2, negative 3.14 plus 2, we have 1.14 of TC is equal to 0. So we can now transpose TC to the other side, maintaining that 0.14 W. So this now becomes positive 1.14 TC. And then finally, solving for TC will be in terms of W. Hence, we have TC is equal to 0.123 W. Okay. Now, we use this expression. Okay, so we have obtained now our objective of expressing TC in W. So the other objective is expressing AB in terms of W. Of course, we can utilize this equation here. Okay, so we substitute TC here, which is 0.123 W, and then we can combine that. Say this remains to be 7 TAB, and then we have negative 3 plus 0.123 of W times 2. So we have here 2.754 W, that's negative. And then solving for AB, we'll just have to transpose that and then divide both sides by 7. So we have TAB now will be in terms of W, that is 0.393 of W. So TC and TAB are all in terms of W. All we have to do is to use the allowables of these two cables. So the allowable for AB and C are both 100. Okay, so we have listed that a while ago, but they have two different cross-sectional area. For AB we have 250, and for C that is 300. Okay, so we better take note of that. So we just say for cable AB, sigma is equal to P over A. 100 is the allowable. Say we just replace the actual force to tensile at AB, and the cross-sectional area for AB is 250. Okay, and the AB is equal to 25,000 Newton. Okay, so we do the same for cable C before we substitute here. Say for cable BC we have sigma is equal to P all over A. We have 100. Say this is tension at cable C, and the cross-sectional area is 300. So tension at C is actually 30,000 Newton. So we use the following allowed or tolerable tension and then substitute on the equations. So first we're gonna do it for tension at C. So say this is 30,000, then 0.123 of W. So therefore, W here is 243,902.44 newtons. And we do similar to this equation for AB. So we have here 25,000 is equal to 0.393 of W. So we obtain a value for W here. We have 63,613.23 newtons. So among this, of course, we're gonna choose this as the safe value for W. Now we are after with the mass, so therefore we need to express that in terms of mass because weight is equal to mass times acceleration due to gravity. So we just have to substitute 63,613.23 is equal to the unknown mass times acceleration due to gravity. So therefore mass will be equal to 6,484.53 kilograms. Okay, so this is the heaviest mass or heaviest weight that we can apply to this system under the premises of the allowables of each of the cables, okay, and the area. Okay, so that's it for this problem. So perhaps we can move on to your seat work today to be accessed in your Google Classroom. So again, thank you for listening and good luck on your exercises. So take it as your practice for today. So that's it.